Thank you, Peter. So the physicists claim Emmy Noether as a physicist. The mathematicians claim Emmy Noether as a mathematician. I think the important thing is that both the mathematicians and the physicists acclaim her, as well as everybody else. So I'm really happy to be here, and I'm going to talk a little bit about Emmy Noether's life and her contributions to mostly algebra, mostly the period after 1920. So just a little bit about Emmy. She was born in Erlangen, Germany in 1882, and her parents, were Ida and Max Noether. So the Austrian mathematician Olga Taussky-Todd, her mother was named Ida also. So judging from a very small sample, if you want to be a good female algebraist, you should have a mother named Ida. Okay, so Emmy had 3 younger brothers. Her brother Alfred got a PhD in chemistry and then died about 9 years later. Her brother Fritz was an applied mathematician who probably many of you have heard of. When Hitler came to power, he moved to Russia, and then in 1941 was accused of being a German spy and was executed. And brother, not a lot about him. He was not very well, and he died quite young. So Emmy decided when she was in her teens and early 20s that she wanted to become a mathematician. The only problem was that she couldn't be admitted to the university. So she audited classes, took the entrance exam, and finally was admitted. So in 1904, there were 2 women admitted to the University of Erlangen. Emmy was one of them. I never found out who the other one was. But no doubt her father had something to do with it, because her father was a very prominent geometer on the faculty. Emmy finished her doctoral degree in 1907 at the University of Erlangen under Professor Paul Gordon, who was a friend of her father's, and she studied computational invariant theory. So many of you maybe know Paul Gordon from the Clebsch-Gordon formula for decomposing representations of SL2. This is the same Gordon. The thesis ended with 331 formulas on invariants of ternary and biquadratic forms. And this is sort of what it looked like. It doesn't look any better in the paper itself. You have to just, even with a magnifying glass, you just can't really even read it. So Emmy's critique of her thesis was, it's just a jungle of formulas. She had terrible things to say about her thing. And of course, nobody really ever really quoted it. But she stayed in Erlangen. Her father had polio as a teenager, and she did a lot of his teaching for him. And she became very interested in approaching mathematics much more abstractly, much more conceptually. And she was particularly influenced by Hilbert's basis theorem, which says for every ideal in a polynomial ring, there exists a finite set of generators. Of course, Gordon didn't particularly react well to this theorem. So what was troubling to him was that it didn't give a way to construct them. You know, it was just existence. And later on, he relented and he said, I see that even theology has its merits. So in 1911, Paul Gordon had retired, and Erlangen hired Ernst Fischer, who was an algebraist and very much aware of kind of an abstract approach to doing algebra. And Emmy really benefited from his presence. In the period between 1911 and 1916, she published papers on invariant theory of forms of n variables, fields and systems of rational functions. Her well-known 1916 paper, Finiteness Theorem for Finite Groups. Okay, so what this is if you take a module for finite group G, and you look at the ring of invariants in the, well, you would normally write this as a symmetric algebra. It's finitely generated, Hilbert's basis theorem. And the invariants generated by invariants of degree less than the order of the group. Okay. So here's just a quick example. If you take the permutation module for the symmetric group, so this is just a basis of n elements, and the symmetric group is just permuting the basis elements. And you look at the ring of invariants, that's just the ring of symmetric functions on n variables. And the generators for this ring of symmetric functions are just the elementary symmetric functions. So you have degree 1, 2, up to n. So she had this kind of wide generalization of that result. And this work was kind of a bridge because there were people like Frobenius, Schur, later Richard Brouwer, who were doing group representations, particularly focused on things like the symmetric group, the general linear group. And so this was kind of her bridge to connect to that group of researchers in Germany. In 1915, Emmy was invited to Göttingen by David Hilbert and Felix Klein. She was given the problem that Karen talked about, Noether's problem. And in this paper, that's the title of this slide, that Karen said she read, appeared Noether's theorem. So this is the abridged version. To every invariance or symmetry property of the laws of nature, there corresponds a conservation law and vice versa. So as Karen was mentioning, it's a very delicate question about what symmetries, even more delicate question about what's conserved, and even more delicate question about what's vice versa. Okay. So after this work, she pretty much threw herself into ring theory. There's a paper before this one that she wrote with Schmeidler, where she defined such notions that we sort of take for granted, very basic notions like left ideal, right ideal. She's credited with, I think, the first isomorphism theorem is due to Emmy Noether. In this paper, she was very motivated by number theory. She wanted to carry over a lot of the properties of numbers to arbitrary rings. And of course, her famous, if every ascending chain of ideals of a ring stabilizes, the ring is said to be Noetherian. So this is probably one of the highest mathematical honors a person can achieve, to become an adjective. Okay. And not only that, to become a lowercase adjective, because it means that this is all over. And I've seen it, read papers in different languages, and it's exactly the same word. So if R is Noetherian, then she realized that this is really the essential property. Every ideal then is an intersection of primary ideals. So primary just means that if you have a product in the ideal, then either one element is in it or the power of another. The other is in there. It looks a little asymmetric, but remember, this is going on in commutative land, so just flip the factors. For every ideal, there exists a finite set of generators. You can understand where that came from. That's Hilbert's basis theorem in this general context. R has the descending chain condition on prime ideals. So if you have the ascending chain condition on ideals, it has the descending chain condition on prime ideals. Prime here just means that if you have a product of two elements in an ideal, then one or the other has to live in the ideal. And then she went through very methodically, added a few more properties, and just showed then that every ideal is the product of prime ideals. So this is kind of just the number theory in rings, products of prime numbers. Of course, primes are very important because the zeros of prime ideals give an irreducible algebraic variety. For example, if you take that polynomial and graph it, you get these beautiful algebraic surfaces. So a heart with a hole in it. When I first saw this, I thought it was a duck with a baseball cap on it. but maybe we shouldn't do mathematical Warlick tests. But so prime ideals are just kind of the fundamental notion in algebraic geometry. Okay, to quote a nursery rhyme, how does your algebra grow? Okay, how do you measure growth? So there's polynomial growth, what you see polynomials doing. There's also exponential growth. So if you just take the free algebra on two or more generators, then you're going to see the spaces, the monomials of a given length are growing exponentially. And then there's something in between. And Grigorchuk constructed a finitely generated group that did not have polynomial growth, did not have exponential growth. Its growth was a little faster than polynomial, a little bit slower than exponential. And this was an answer to a question of Milner about whether such type of growth occurs. And this group is really kind of one of the fundamental objects in geometric group theory. Now, if you're dealing with algebra, there's another way you could talk about growth, and this is the Gelfand-Kirillov dimension. So you have an algebra that's generated by an algebra over a field, and a finite dimensional vector space. And so you start looking at the dimension of the products of size, length, n. And you take that log and you divide by log n, and then you look at the lim sup of that, and you see, what kind of number do you get? And for polynomials, you get the right answer. Okay. Polynomials in degree in m variables have GK dimension m. And so for example, if you are working with universal enveloping algebras of Lie algebras that have a basis of n dimension, then that will have GK dimension n also. So some surprising results. In 1976, Borrow and Kraft showed that there exists algebras satisfying these hypotheses that have GK dimension alpha for any real number alpha greater than or equal to 2. And then George Bergman in 1998 showed that there are no algebras between 1 and 2. Bergman's gap. So we know the endpoints, right? Polynomials of one variable, polynomials of two variables. There's nothing in between. And then there's a much more recent result by Agathos Maktunovic that said you can't have graded domains. So this is graded and the product is graded, such that the dimension of the zero space is finite and the GK dimension is between 2 and 3. So it just starts to indicate how little we know about how things are growing. And you can ask really basic questions. If A is Noetherian, is the GK dimension finite? I think you have this, limiting chains of ideals. Does that somehow force the growth to be finite? Sorry. Is the GK dimension of a Noetherian ring an integer?
Similar questions for von Neumann.
Algebras.
All false.
Pardon me?
Where everything goes bad.
Everything goes bad. So it's known in that case?
These kind of
Yeah, okay. Okay. So probably in the last 20, 30 years, there's been kind of a push to try to create a non-commutative algebraic geometry. So in the commutative setting, if you have a commutative projective variety embedded in projective space, you have the homogeneous coordinate ring commutative. So what do you do in the non-commutative setting? So this is kind of a direction some research has been going of if you take A to be a non-commutative projective curve or surface, well, we'll say that it's a non-commutative projective curve or surface if it's a graded algebra. The GK dimension is 2 or 3, 2 if it's a curve, 3 if it's a surface, and A is a Noetherian domain. Sort of bypassing the geometry and going right for the coordinate, right for the algebra. And there's a conjecture by Michael Artin in 1995 that gives some idea of the kinds of things that are expected to come out. So if A is a non-commutative projective surface, let's let D of A be its quotient division algebra. So it's a domain, so we can form its quotient division algebra. Just division algebra quotients. Let's let K be the center of the field, of this quotient division algebra. It's a field. Then his conjecture says that either D of A is a finite module over this field, K, the center, and the transcendence degree of K is 2. That's over the original field. Or this quotient division algebra is a field of fractions twisted by either an automorphism or a derivation. And the transcendence degree then would be 1. And the final conjectured type is that this division algebra is the division algebra of a Skleanan algebra. So we're working in surfaces, so it's got something to do with things with 3 generators, and then these very unusual equations, cyclic permutation. So as far as I know, there's no known counterexample to this conjecture. There's no known proof yet. Okay. So we're going to get some kind of non-commutative geometry. Should be looking at algebras that kind of have these properties. There's a notion of an Artin-Shelter regular algebra that comes in here and is related to these conjectures, but I'm not going to talk about it. Okay. Starting about 1926, 27, Emmy threw herself into non-commutative things. This is Wedderburn, and this is his famous theorem, structure theorem, from 1907. That says if you have a finite dimensional algebra over a field K that's central, so the center of A is K, then there's a nilpotent ideal, modulo which it's just the direct sum of finitely many matrix algebras over division algebras. And the division algebras also have as their center K. So Wedderburn was a professor at Princeton for quite a long time, most of his career. He's my mathematical grandfather. Maybe you notice the resemblance. But,
Was he a student named Ida?
Who needs Ida when you have a grandfather like Wedderburn? Okay. So Leonard Dixon, Wedderburn spent 1 year at the University of Chicago studying with Leonard Dixon. And Leonard Dixon in 1906 introduced the notion of cyclic algebras. So let L be a finite cyclic Galois extension of a field K, so the Galois group is cyclic. And take the product of these two, the field extension and the group, and then make this into an algebra. So this U is sort of representing the powers of sigma, or is representing sigma. And so we've got finite sums of terms, A, U to some power, and then it's not commutative because when I move an element of L across, I apply the element of the Galois group, and then U to the N is just some element of the field. So this was a really interesting construction of algebras, and people thought, well, we really can focus on division algebras up here because it's very difficult to say anything about that nilpotent ideal. And in fact, when this algebra acts on anything, that nilpotent ideal acts as 0. So we should focus our attention on division algebras. We need some examples. What Dixon's method gave was a way of constructing examples of division algebras. In 1923, Dixon wrote a book called Algebras and Their Arithmetics. And I think this was one of the first times that the Germans sort of got an idea of what the Americans were working on. In fact, some of Dixon's work. And it inspired a lot of work by Emil Artin, Richard Brouwer, Helmut Hasse, and Emmy Noether. And the question arose, is every central division algebra over an algebraic number field cyclic? Can we construct it that way by that process? In 1930, Brouwer published non-cyclic central division algebra, but it wasn't over an algebraic number field. So the question was still out there. And then in 1932, Brouwer, Hasse, and Noether published the result that every finite dimensional central division algebra over an algebraic number field is a cyclic algebra. This paper has kind of an interesting history to it. So Hasse was the editor of Kreller's journal, and he accepted the paper. Now, the reason, well, I think there were several reasons for this. One was the paper was dedicated to Hensel for his 70th birthday, so there was a bit of time pressure because of that. But there was also a bit of time pressure because after Dixon's book appeared, there was a lot of communication with people on this side of the Atlantic, and especially between Hasse and Albert at the University of Chicago. And they sort of realized that they're working on the same thing. And so there was, I think, a bit of pressure to get a priority for the result. Then to complicate the matter a little bit more, a few months later, Albert and Hasse published another proof using more the ideas of Albert in transactions. Pardon me?
Hasse was on both?
Hasse?
Hasse was on both, but he's an author on both.
He's an author on both. Albert primarily communicated with Hasse. So here are a few of the key ingredients in the proof. The first thing was the notion of a splitting field for a central simple algebra. So you have a simple algebra, no ideals, finite dimensional over a field that's the center. There's a splitting field extension so that when you tensor with that or extend the base field to L, it just becomes isomorphic to matrices over L. So if you think about what this would be saying for division algebras, over the reals, the division algebras are what? The reals, the complex numbers, and the quaternions. And if you extend the base field to numbers, the quaternions become isomorphic to 2x2 matrices over the complex numbers. So the complex numbers are the splitting field for the quaternions. And Brouwer and Noether realized that they were both basically working on the same thing, working on proving this. And so they joined forces and actually published the existence of splitting fields jointly in 1927. So that's one ingredient. Other ingredient is what's called the local global principle. States that a central simple algebra over an algebraic number field splits over K if and only if it splits everywhere locally over all localizations of K at primes P. So what's going on here is you're looking at algebraic integers over K, the ring of algebraic integers over K. You're looking at the prime ideals of those, and you're localizing at those prime ideals. So it's the local global principle. Emmy was very involved with localizations. But really, there was a lot of kind of p-adic analysis going on with the kind of thing that Hasse worked on. And then there's Grunwald's theorem. People know this theorem? There exist cyclic extension fields of algebraic number fields. Obviously, if you're going to prove things are cyclic, you need a cyclic extension field. So Artin, in a letter to Hasse in 1931, sort of knew ahead that they had proved this theorem, said, "You cannot imagine how ever so pleased I was about the proof. finally successful for the cyclic systems. This is the greatest advance in number theory of the last years. The quote is very ironic. Because a graduate student of Emil Artin spent about 10 years at Princeton, so between mid-1940s to mid-1950s. Graduate student Xiangsha Wang published a short note in Annals. In recent research, the author of this note found that Grunwald's theorem on the existence of cyclic extensions over an algebraic number field was not always true. On the other hand, he has obtained a proof of the theorem under appropriate restrictions. Here, a counterexample will be given and existing proofs analyzed. Okay. So, of course, now that whole result is kind of in limbo because you don't know whether the restrictions are going to be able to, you're going to be able to prove the theorem, the Brouwer-Hasse-Noether theorem. So, pardon me?
What year had they? How many years was this?
So this was 1949. So that was like about 18, 17 years earlier. So it kind of existed for a long time. So Wang, in a 1951 volume of Annals, proved a version of Grunwald's theorem, now known as the Grunwald-Wang theorem, which maybe some people have heard, and was sufficient to give a cyclic splitting field for each central simple algebra over an algebraic number field, and that's really was what was needed. And so the theorem is basically that a central simple algebra over an algebraic number field is a cyclic algebra. So Emmy moved on from this to looking at cross products, or if you like the German, Verschränkte product. Sounds much more dramatic in German. Okay. And she developed the notion of a cross product and results about them. Like many things, she sort of gave things away. And Hasse published the construction, the cross product construction and transactions, 1932. With Emmy's permission. Amazing.
Neither was a student of the other. They were just,
No, neither were. They weren't, connected that way.
I don't know who
Gordon was. No, I'm not sure who Hasse was a student of. Was it Hensel? I would guess it's some kind of number theorist. So the construction is you take a finite Galois extension of a field K with Galois group G, and you take, again, the product, elements of L, elements of G. This time we're going to subscript them because we don't just have a cyclic group. And you basically write down the same thing we saw for cyclic algebras, that as you move something across one of these group elements, it gets twisted by the element of the Galois group. And then when you take the product of two elements that are grouped, like you get this kind of fudge factor here. And then you show that the algebra is going to be associative if it satisfies this cocycle condition. So then there's this notion of the Brouwer group, and this is equivalence classes of central simple algebras over K. So if an algebra is central simple, that means it doesn't have any ideals. So it's going to be isomorphic to matrices of a certain size over a division algebra. And if you have two such things, then the equivalence classes are, this class is equivalent to this one if the division algebras are isomorphic. And this forms an abelian group under tensor product. Okay. So what's the identity? So what we're basically doing is what? Erasing matrices and focusing on the division algebras. So the identity here is going to be the equivalence class of matrices over the base field. What's the inverse? Well, if you have a central simple algebra, the opposite algebra is also central simple, where you switch the order of the products. And if you tensor the two of them, you get a matrix algebra. So it really forms a group. Very interesting group. And in 1932, a lot happened in 1932, an amazing amount of mathematics. Emmy Noether showed that the classes of central simple algebras over K, having L as a splitting field, form a subgroup of the Bauer group. Not only that, but in modern terms, that subgroup is isomorphic to the Galois cohomology. The cohomology, the group G, with coefficients in the non-zero elements of the extension field. Now, what's really kind of fascinating about this result is that on the right-hand side, that's just number theory, basically. Field extension Galois group. On the left-hand side, this is non-commutative algebras. So her whole point was that non-commutative algebras really can say something about number theory. So she also realized that these cocycles had something to do with topology. That group cohomology, which is what's really going on here, really had an important role in topology. And she started urging her good friends, Paul Alexandrov, who spent 3 years in Göttingen, and also Emmy visited in Russia, and Heinz Hoff, to use algebra, particularly group cohomology, to solve problems in topology. So her philosophy was, do away with computation, use algebra. Okay. None so virtuous as the converted, right? So she was really urging them to really go ahead and create algebraic topology. She took this message to the ICM. She gave an invited address at the 1932 International Congress of Mathematicians in Zurich. This is the paper that she published based on her lecture. It's a little hard to read. The title is here. What it's saying is hypercomplex systems. So that was the German term for algebras. So you start with the complexes, then if you have things of higher dimension, those are hypercomplex, hypercomplex systems. Algebras in their connections to commutative algebra and number theory. So she's really pushing the message that non-commutative things, the Bauer group, algebras, have a very important place in studying commutative algebra and number theory. And she sort of backed that up with that paper where she was using cross products. So 1932 was an amazing year for Emmy Noether. She was one of 21 invited speakers at the International Congress. She also won the Alfred Ackermann Tobner Prize jointly with Emil Artin. And then 8 months after the Congress, she was dismissed from her position. So when the Nazis came, she lost her position. This was at her position, the title of her position. Okay. Roughly translated, it's associate professor with teaching privileges. And then it should have a little footnote that says, and with a very small salary. So when the political situation got it degenerated, Emmy left Germany and went to Bryn Mawr College. And there were a lot of people who worked to make that happen. The Rockefeller Foundation, people here at IAS. Richard Brouwer went to the University of Kentucky. Hermann Weyl came here. Einstein came here. Tuesdays, Emmy would come to IAS from Bryn Mawr. I was just talking to some people from Bryn Mawr and said that must have been a pretty big trip because it was by train about 2 hours each way. But she met up with her friends, her collaborators. Hermann Weyl was a very dear friend, colleague at Göttingen. And it was sort of like, you know, this is my day to do research. This is my day to recapture what I had in Germany. In 1934, Abraham Flexner and Oskar Veblen invited Emmy to give lectures. So 1 2-hour lecture every week on Tuesdays. Okay. I hope they had tea in between like we did. And she lectured on class field theory. This was supposed to be the academic year 1934 to 1935. In the spring of 1935, she announced to the class that she'd have to take a recess because she was going to undergo surgery. And she actually died 4 days after the operation from complications of the surgery. So I was also talking to the Bryn Mawr folks who told me something I didn't know, that Emmy's ashes sat in the office of the president of Bryn Mawr for 100 years before they were buried. Or not 100 years, sorry, 1935 to 1982, so 47 years. Sorry. Anyway, she left just a tremendous legacy of mathematics. She inspired many people, mathematicians, physicists, with her mathematics, with her physics, and I think most of all with her life. So thank you very much.